It's my pleasure to introduce Mike Staudenmaier and Kim McMahon, who will be talking about NWS HeatRisk Experimental for the regional webinar for Central Region. It looks like Kim will be starting, so go ahead, Kim.
Thanks, Mike. Good morning, everyone. I'm Kim McMahon. I'm the National Weather Service Public Weather Services Program Manager, and welcome to this webinar, Experimental Weather Service HeatRisk. During this webinar, we're going to provide an overview of this exciting new tool with a central region focus, and we'll also look at how HeatRisk works, how it can be used, and we'll look at some verification and additional resources available to you and your partners. As Mike stated earlier, this webinar is being recorded, and by attending, you consent to the recording of your likeness. After the webinar, the recording will be available on our public program Google Sites at the URL shown on the slide. So please keep your lines muted until the question and answer period at the end. And today with me, I have the privilege of introducing Mike Staudenmaier, who is the Division Chief of the Western Region Headquarters Science and Technology and Fusion Division. Mike and his team developed the initial approach to HeatRisk in 2013, and he continues to lead the development with its latest release. We'll focus on experimental HeatRisk in this presentation, but I just want to remind everyone that this is just another tool in the toolbox of weather service forecasts to assess and message the forecasted heat. So Mike, I will pass it on to you.
All right, thanks, Kim. Since many of you already should have some understanding of HeatRisk, hopefully you do. If not, there's training. The VLab or the public page has a lot of information on it. And for the sake of time, I'm just going to review a few of the high-level aspects of HeatRisk philosophy and the five-tiered structure. But I don't want to dive in too deep so that we have time to walk through more of the interpretation and use of the HeatRisk forecast and climatology elements. Experimental HeatRisk is a color number-based framework that compares the forecast temperatures against scientifically derived thresholds to provide an index of the potential risk for heat-related impacts. We developed it to be as easy to communicate as the air quality index or the UV index, which expresses complicated information in an easy to understand approach. And as we'll talk about, the science going into HeatRisk is somewhat complicated. I want to reiterate that HeatRisk is a framework, and the underlying science can always be modified down the road should we wish to, without compromising the simple color and numeric messaging approach. When we started development work, we did a lot of peer literature review looking for nationally valid heat health findings which could inform our approach when we developed HeatRisk. For example, research showed that communities adapt and build to their local climatology, so we built in 2.5 kilometer resolution climatological information. Research showed that acclimation occurs on a time scale of a week or two, so we've created thresholds that change over that time scale, similar to how the normal climate curves change at each location. Research has also shown that some level of heat can be physically dangerous to the human body no matter the time of the year, but it also suggested that everyone has different heat tolerances, so this means that a single threshold wouldn't work for everyone. So we built a 5-color and number system into the approach to provide information specifically for a variety of heat-tolerant groups. Research also showed us that the use of the 95th percentile of temperatures to identify heat episodes that are excessive for a particular location was somewhat common throughout many studies and heat health warning systems across the world. So that's what we used. Because of the desire to have high-resolution output that was still skillful out to 7 days and beyond, we based the system on temperature, since temperature is the first-order driver for heat impacts, and we have the most station observation data sets available for temperature. While we recognize that other items like wind, humidity, and clouds are important secondary drivers, there were quite a few obstacles in our way to use them directly. First, there were no 2.5 kilometer daily wind or cloud climatological grids available to generate what is unusual, nor are there solid national rules on how to apply those to adjust for heat risk. Second, we just don't have that many official weather stations that report routine dew point temperatures with a period of record that goes back 30 to 50 years in order to calculate a skillful 95th percentile of heat index. Third, forecasting hazards like wind, dew points, and clouds are pretty challenging beyond the short-term period, and that limits our long-term skill. So while these weather elements are important, we recognize that the most skillful parameter you forecast, temperatures, really drive the bulk of negative heat impacts. We can, however, roughly estimate humidity and air mass characteristics by leveraging temperature ranges and minimum temperatures. The last thing I'll mention here is that in order to be consistent across the CONUS, the same framework rules need to be applied in a similar fashion to all locations. While any method can be tweaked to be better for any particular location, a national approach can't have local rule sets imposed within it without the heat service becoming inconsistent. So here you can see all the factors that are considered in the heat risk approach. Both high and low temperatures play a role in predicting the 24-hour value. The thresholds identifying the various levels of heat stress change through the year based on local climatology to better account for acclimation. The entire 7-day period is examined to identify periods where excessive temperatures exist for 2 or more days. The likelihood that accumulated heat stress generated during the daytime would be mitigated or maintained overnight. And HeatRisk is the first national scale, high resolution US heat forecast tool to incorporate national heat health data within it, informing us of what temperatures are at levels that pose an elevated risk for heat-related health complications. All right, this isn't my area of interest, obviously, or skill, but let's talk a little bit about the CDC heat health relationship data. While the roots of heat risk began as a purely climatological framework, in 2016 to 2018, we began working with the CDC to incorporate actual heat health impacts into the approach. The CDC has access to not only peer-reviewed heat health modeling approaches that are state-of-the-art, but also to national heat health data that would be needed for the approach. After initial proof of concept testing looking at both mortality and morbidity data relationships, we settled on using mortality data because at that time, this was the only heat health data set that was available for all CONUS states at the county level. Using this list of available counties, we provided the CDC with the best observation station with continuous daily data from 2004 to 2018 within each of those counties to base the relationship on. This provided us with around 700 city-county pairs ranging from large urban areas down to rural locations. I don't have the time to get into the specifics of the epidemiological methods that were performed, but these are considered state-of-the-art methods within the heat health community. Mortality-based exposure response profile curves were generated for both max-T and min-T. Air pollution, seasonality, long-term trends, and day of the week were just some of the parameters that were controlled for in the model. Lastly, health impacts were estimated for a cumulative lag period to account for the delayed effects associated with heat exposure. A second stage was needed to iron out stability issues, especially in areas that were affected by sample size issues. Think of the second stage modeling as a way to smooth out imprecise exposure response relationships due to sparseness of data. The bottom line here is that this approach to generate these relationships is far superior to what we could do by just simply collecting mortality data statistics from local hospitals and basing relationships just on those limited data sets. Here is an example of a temperature mortality relationship for a single county city pair. Briefly, the y-axis denotes health risks and the x-axis denotes temperature. The area to the left of the blue vertical dashed line in the middle is called the no-risk zone, where the effect of heat exposure is not observed. The area to the right of the blue vertical dashed line is the heat-sensitive risk zone. The yellow dot represents the minimum mortality temperature, which is the temperature at which the effect of cold is not observed and the effect of heat starts to increase. And the gray area represents model uncertainty. So both warmer and cooler climates could have similar shaped relationship curves as we see here for the upper two graphics, but underlying exposure patterns and the resultant heat attributable death characteristics can be totally different. In hotter climates, we may see heat attributable deaths increasing with increasing temperatures, but in cooler climates, extremely hot temperatures are much more rare, so that heat exposure occurring at moderately hot temperatures could result in greater adverse heat health outcomes overall. So the CDC combined the health risk information with person days of exposure to develop a distribution of heat attributable deaths over a range of temperatures, which are represented by the bar graphs here in this example. Note the difference in characteristics between these two locations. The first step was to translate all of this epidemiological analysis into actual values that the National Weather Service could use on a heat risk approach. Ultimately, the metric we settled on was the percent of heat attributable deaths, or PHAD. This metric provided us with a range of percentages that total to 100 between the minimum mortality temperature and the maximum temperature observed at the station. From that distribution, it's just a mathematical exercise to derive the specific percentile temperatures shown here, which were used in the creation of the heat risk thresholds. All right, let's get back to stuff that I know more about. Let's talk briefly about the 5 heat risk categories that we use in the approach. The worst category is the extreme level. We color it magenta and it's numbered level 4. I'll let you read the full text here, but the main takeaway is that this level is triggered when afternoon temperatures are very near or above all-time record values, or more commonly, it will be triggered when there are 2 to 3 consecutive days where both the maximum temperature and the minimum temperature contributions are in the red category. We trigger it on 3 days for warm climates and on 2 consecutive days in cooler climates where long duration heat waves are less common. The next category is the major level, colored red and numbered level 3. Again, you can read the words here, but the important takeaway is that there really isn't much difference between magenta and red days. Both magenta and red level events represent something in that top 5% of hottest days and nights in the climatological reference period for a location. But either the duration criteria or the extreme maximum temperature criteria weren't met for the red criteria to be augmented to magenta. Both categories are potentially very impactful. I'll just make a few points about the orange category in this slide. This category will primarily negatively affect those populations and sectors who are at a higher risk in category. It's important to keep in mind that most of us go from air-conditioned cars to air-conditioned work, gym, or home, and would view these days simply as warm or uncomfortable. But since we stay hydrated and cooled, we really aren't at that much risk. But those populations who are unable to take those preventative measures or are more sensitive to heat would potentially be impacted by these lower temperatures. It's also important to realize that even those of us who are normally heat tolerant can become one of those at higher risk populations when we don't adequately hydrate or stay cool during the heat of the day, such as when attending an outdoor venue or participating in strenuous activities outdoors without taking proper precautions. We see many instances of heat exhaustion or worse occurring at outdoor venues or sporting events during the summer on orange days amongst otherwise healthy individuals because of this. I'm assuming the vast majority of you have already heard about how the heat risk daily thresholds are derived, but I'll review it briefly on this slide. This chart is something that's available to all CONUS WFOs as a visual means to see the daily thresholds for the entire year. This example is for max T for the Kansas City International Airport. The x-axis denotes the months of the year, and the y-axis is temperature. The black stair-step curve denotes the daily NCEI 1991 to 2020 normals for this location. The lighter gray stair-step curve denotes the smooth 95th percentile curve derived from a standardized period of 1970 to 2020. The dots on the map represent the daily record high temperatures for the station during the entire period of record. The yellow line is based on that minimum mortality temperature we just talked about, where the effects of heat begin to occur. For rural locations, we utilize the first percentile temperature in order to have a slightly higher temperature to represent the more resilient populations that are in rural areas. Moving to the red curve, the flat part of the curve is derived from the 50th percentile of CDC heat attributable deaths. This represents a temperature where 50% of the mortality was modeled to occur at and above this value. An even more important thing to keep in mind is that 50% of the modeled mortality occurred at cooler temperatures than this. We chose this intermediate value to not overwarn, but still provide good values that would make a positive difference to meeting our National Weather Service mission of protection of lives, property, and enhancing the economy. When this threshold encounters the 95th percentile curve, the daily red thresholds will then follow that curve, which is our way of acknowledging acclimation among heat-tolerant populations. The orange curve is an intermediate value between red, yellow, and the normal curve. The orange portion of the chart represents lower temperature values that would still be of danger to those at higher risk populations and heat-sensitive sectors. We also provide an acclimation aspect to orange, but we cap that acclimation value at the CDC 50th percentile value, or the red shoulder value, because it's likely that many of the heat deaths that occur in the summer continue to be within the at higher risk populations. The fall shoulder flat area of the orange curve is higher at many locations to represent the more resilient population that remains after the heat of summer. This value utilizes the 25th percentile of heat attributable deaths from the CDC data set. We know this all sounds really complicated, but heat health science is complicated, and hopefully you can appreciate how much heat health science is considered in this approach. So at this point, we've now defined all the daily thresholds for our example location. As this example chart shows, on any given day, this location has unique daily thresholds for yellow, orange, and red, which can then be used to put the forecast temperatures into heat-related context. In this example, on July 15th, the yellow threshold would be 73, the orange threshold would be 92, and the red threshold would be 99. We follow a somewhat similar approach for minimum temperatures, leveraging the CDC data for the yellow threshold again, but we solely leverage climatological data for the orange and red thresholds. This is for two reasons. The first is because the CDC didn't find a strong relationship between their health data and minimum temperature independently from max-T for us to use their model thresholds exclusively. So we use the minimum temperatures to identify those situations where climatologically unusual overnight heat contributes to maintaining or even increasing the heat stress that accumulated during the daytime period, or if instead cooler minimum temperatures would instead lower that risk. The second reason we include minimum temperature in the approach is because we can leverage the general correlation between elevated humidity and elevated minimum temperatures, which, as we all know, is a core concept we learned in Meteorology 101. We leverage this relationship in a few different ways in the heat risk approach. One area we do this is by lowering the red spring-fall shoulder values for min-T in more humid climates, and we raise them in more arid climates to better account for the role of humidity. We carry the same process to calculate the maximum and minimum temperature thresholds at about 3,100 individual stations across the country that have high quality, long duration, consistent climate data, which have passed our QC process. We then use PRISM high-resolution climatology grids with this point data to develop daily gridded red, orange, and yellow thresholds over the entire CONUS. This science-based approach leads to very different annual threshold curves at each location, and this is what we want. Here you can see an example for both the Lincoln Airport in Nebraska and downtown Los Angeles, showing how these thresholds increase during the spring, they peak, and then they drop during the fall. But the values and even the curve shapes themselves are very different in order to represent that climatology appropriately. All right, the 700-pound gorilla. So we know humidity plays an important, though secondary role in heat impacts, especially across the eastern United States. In fact, there's strong evidence to support the 100th meridian as a natural divide between the humid east and the arid west, as shown in vegetation and rainfall. This is also true for the peak average dew point. So there's compelling evidence to support making different moisture adjustments within the experimental heat risk algorithm for locations east and west of this divide. And that's just what we do by splitting the country up into either a humid east or a more arid west. So let's dive into this humidity accommodation just a bit more, as I know it's a huge concern for you all out east. The heat risk algorithm leverages a term we call the diurnal range modifier, or DRM, which is simply the highest daily maximum temperature in the annual curve minus the highest daily minimum temperature in the annual curve. We calculate this value at all grid boxes. Locations with humid climates exhibit a smaller DRM range. Heat risk leverages this natural humidity dividing line in the middle of the country and the DRM to define the areas where we'll apply one of two 24-hour equations. Within the transition zone of 104 west and 97 west, we define the area where the DRM is less than 27 degrees to utilize the humid heat risk 24-hour equations. Areas where the DRM is greater than or equal to 27 degrees would utilize the dry heat risk 24-hour equation. All areas west of 104 would also utilize the dry equation, while all areas east of 97 west would utilize the humid equation. After filling in some islands in the transition zone, this results in a meandering border between the transition zone that roughly approximates this transition between moist and more arid climates that was recognized well over 100 years ago. As mentioned earlier, we also utilize the DRM to adjust the red Min-T shoulder threshold value up in more arid climates and down in more humid climates to, again, provide a better approximation of humidity in the approach. So let's talk about how we create the overall 24-hour value of heat risk, which is the final output of the approach. First, we assign a 0, 1, 2, or 3 to the individual max T and min T forecast temperature values based on where they fall within the daily red, orange, and yellow thresholds for that location. We then combine those values coming from the morning min T, the afternoon max T, and the following morning's min T to create the 24-hour value using one of two equations. For humid climates, where humidity plays a significant role in modifying the feel-like temperatures, the combination involves having the minimum temperatures on either side of the afternoon high providing 55% of the 24-hour value. The contribution from the afternoon high accounts for the other 45%. In dry climates, the impact of heat stress from the afternoon temperatures is generally much more substantial than that from humidity. Therefore, the contribution from the max temperature gets the greater weight, in this case 67% of the overall 24-hour value. The minimum temperatures provide the other 33%. We apply a bit more logic to fine-tune that final 24-hour value, especially out east, to again better account for humidity, and then we round it off, and the integer value is the final result. Okay, let's go through a couple of quick examples working through the 24-hour equations. We'll focus on Des Moines, Iowa for this. First, we can demonstrate that time of the year matters. In this example, the heat index is 95 for both June 1st and July 15th. And the high and low temperatures are exactly the same in this example. But in the early part of the year, we see that the lows of 71 and 72 would both contribute to a value of 2 to the 24-hour equation, and the high of 94 would contribute to a value of 3. Applying the ratios we described, a 24-hour heat risk value of 2.45 is calculated, which is very near the upper portion of the orange category, since we round values of 2.5 and higher to be colored red and assigned an integer value of 3. Because of the early time of the year and the max T value being in a red category, heightened messaging or perhaps an advisory would be warranted. However, using those same values in the middle of July results in a yellow 24-hour heat risk value of 1.45, which essentially is indicating that these temperatures are not that unusual for this time of year in this location. So you can see that heat risk takes time of year into consideration to place that heat into climatological context. All right, let's look at how the role of humidity can be roughly accounted for in the approach. Let's say that on the 17th of July, a bunch of moisture moves into the area with dew points increasing into the mid-70s. Overnight lows stay elevated at 77 degrees, and the daytime high is the same as it was on the 15th in the previous example. Now, when we plug in the contributions from min T of 3 for each of those values and the 2 for the max T contribution, we get a non-rounded 24-hour heat risk value of 2.56, which is in the red category. This is much higher than what was obtained when the heat index value was 95 just a few days earlier. In this case, the calculated heat index value for the situation resulted in a value of 105. Hopefully you can see how heat risk is sensitive to higher dew points and humidity through the use of the min temperature contributions. All right, stepping back, here's a look at the full process. You should now have a pretty good understanding of the broad strokes of what heat risk is and how it works. In a nutshell, we use the CDC heat health relationships and local climatology to generate data at over 3,000 points. We then use PRISM to develop 2.5 kilometer daily grids for the yellow, orange, and red thresholds for both max T and min T. Those daily thresholds are compared to the NDFD temperatures at each grid box with a max T and 2 min T integer contributions going into one of two equations. This results in a daily 24-hour experimental heat risk grid for the 7-day period. Since heat risk was initially developed in the West, people always ask me, how does heat risk verify everywhere else? As you know, heat risk was developed using mortality data thresholds. So with heat risk going CONUS-wide, we wanted to test the approach using independent data over 5 full heat seasons to generate long-term verification. So we examined CDC-provided emergency department heat-related injury data, which in this example is expressed as a rate per 100,000 emergency department visits overall. These data are organized into 10 regions across the continental United States based on FEMA regions. For each of these regions, These daily heat injury data counts were compared to the daily average observed heat risk values using all of our approved NCEI points in each FEMA region for the full heat seasons from April through October 2019 through 2023. You can see that each FEMA region has its own chart plotting the data, including a logarithmic correlation with FEMA region 10 in the upper left and FEMA region 1 in the upper right. The center map shows the date with the highest impact rate during that entire 5-year period, which occurred on June 28, 2021, when the Pacific Northwest suffered from a historical and devastating heat wave, and the Northeast US had a significant heat wave concurrently. So what were the results? We in the weather and climate world get pretty excited when we see correlation scores above 0.6. I know you can't read the values, but these 5-year correlations between heat risk and the injury data set across all regions were well above that, with the lowest correlation score being 0.80 in FEMA Region 1, and the highest correlation score being 0.90 in FEMA Region 6. 5-year correlations in all of the FEMA regions within Central Region were between 0.80 and 0.90. This is a great indicator of the utility of heat risk, not just for the big warning days, but for all those other times when less widespread but still important heat-related impacts are happening. Is it perfect? No. But this independent data does show that heat risk did quite well over a 5-year period across the entire country, not just in the Western United States, in identifying the bigger events in each region. It also shows that even without directly utilizing heat index, it provides a skillful means to identify the days when many people were going to emergency rooms for heat-related injuries from those other less impactful days. There's several tools available to the local meteorologist in the form of grids within the local GFE. One of these is a product recommender, which provides a zone-based recommendation to issue a heat product or to consider the situation more closely for the potential of issuing a product based on the mean 24-hour heat risk value in that zone. We've been using this approach in the Western US for over 5 years now. These recommendations are based on utilizing those pre-rounded non-integer results from the 24-hour equation, leveraging those values between 2.0 or the mid-orange category up to 4 or magenta. The entire range of orange heat risk are not utilized in making a product recommendation or consideration, as that would lead to product fatigue. But heat risk will likely make more recommendations for action than our traditional thresholds due to an enhanced focus on those more at-risk populations. Also within the GFE are Hill Max T and Hill Min T grids, which essentially are the gridded integer individual contributions that are going into those 24-hour equations. These grids allow you to see a bit into the process prior to the final outcome. We found that these grids help a bit with interpreting the final heat risk value and tailoring your heat messaging. For example, we'll frequently include messaging to move activities to the cooler part of the day, or that the use of fans and opening windows at night will be adequate as some of our call to actions. But if the Hill Min T grids are red, this indicates that temperatures are something like in the top 5% of the warmest nights at that location, and those actions will likely not be adequate to reduce the heat stress built up during the daytime. But if those Hill Min T grids are yellow or maybe even orange, that type of messaging may be quite appropriate. So what about this consider recommendation? Because impacts can and do occur with just a moderate or orange 24-hour value, we found that heightened messaging or even the issuance of a heat product can still be warranted. This recommendation is provided to the meteorologist to consider other items in their decision. Is it early in the season? Is this an area where we have less air conditioning use? Is it occurring over a weekend with large outdoor venues going on where more people will be put into a heat vulnerable population? Is this just a brief cool down between two excessively hot periods and we should bridge that slight decrease in temperatures with a product due to the known lag factor of heat impacts and also to keep the overall heat event intact? Are there widespread power outages in the area? Are heat indices high enough to warrant issuing a product or provide enhanced messaging even at this orange level? This is what should be considered when the product recommender grid is providing that recommendation. As an example of the benefit of including heat risk in the heat watch warning advisory product process, I provided a 7-day loop of daily heat risk values forced by the day 1 NBM during a significant heat wave in August 2023. You can see that on the right-hand side. The white polygons are the National Weather Service heat products issued independently using a heat index approach. While every week last summer didn't show this type of good matching, many weeks were pretty similar in behavior where our WAWA heat products were issued in areas of orange, red, and magenta heat risk. As mentioned, HeatRisk wasn't specifically developed to reproduce heat index thresholds or to only support the issuance of our traditional heat products. The use of HeatRisk with heat index knowledge should ultimately be used together to make the best heat messaging decisions. But HeatRisk does a fairly good job in identifying those higher heat index days to occur within the higher half of the orange category and through the red and magenta categories. To illustrate this another way, let's look at another one of the climatological charts that are available at the local office. These annual charts show each observed max T and min T observation value colored based on their integer contribution to the 24-hour equation and annotated as a dot for the max T and a star for the min T. At the bottom, the color of the 24-hour value is provided on the strip chart. In the upper right-hand corner, we have provided what the algorithm would have generated at that location for heat product recommendations using the observations. This example from Minneapolis-St. Paul International Airport for 2021 has a list of dates where heat products would have been recommended, along with a handful of dates that the algorithm would have recommended that the meteorologists consider other factors to determine the appropriate action. The bottom chart, which isn't available to you, comes from our development activities in 2022, when our big focus was tuning heat risk to better approximate the big heat index days. That chart has a normal curve of daily heat index in blue, a 95th percentile curve of heat index in black, along with a daily hourly maximum heat index value as dots colored according to various heat index ranges. The top 10 box provides the dates and value for the top 10 heat index days in that year. I'll leave it up to you to cross-reference the two, but HeatRisk has all 10 of the dates of observed high heat index within its recommendation and considered date ranges. I'll also note how HeatRisk identified the early June episode as particularly dangerous, even though the overall heat index values were a bit lower than what occurred later in July. This was due to a combination of early season heat, multiple consecutive days of temperature being the top 5% of what's observed that early in the year, and minimum temperatures that were ridiculously high for any time of the year. While we picked this one example to show you, we observe this type of relationship generally at the other 40 Eastern United States sites that we used for this development activity in 2022. It can be challenging to verify heat risk locally. Since the approach really is focused on identifying those top-level heat events using a 95th percentile approach, heat risk pretty much will verify as well as the temperature forecasts do. One common issue that we do see in heat risk forecasts is an under-forecasting at longer lead times due to the conservative nature of our forecasts. While we tend to spend more time on maximum temperatures and have good skill at predicting those, we sometimes tend to underestimate how warm overnight minimums will be, and that can have a pretty big impact on the heat risk forecast. When you drill down to local and county level data sets, some of those impacts are not going to be nice and linear and well aligned with heat risk. Overall, it's pretty unfair to expect any national approach to work for any and all user groups and impact data sets. So expect to see some data sets and locations where data don't line up perfectly with increasing heat risk. You saw in the CDC modeling section how some areas have more heat attributable deaths occurring at cooler temperatures versus the very hottest. We also see that kind of behavior when we compare winter road accidents and snowfall. Many more accidents happen on lower snow threshold days than at the extreme major storm values. The bottom line is that impacts due to any weather hazard are intertwined with many other human and societal factors that make the data sets more messy to deal with as they get more localized. That's why we verify heat risk with national data sets when possible, to get the bigger picture of how it's verifying with a long enough and a robust enough data set to iron out kind of those local issues. The example graphics on the right show two very different results when comparing a specific local impact data set with a station-based heat risk climatology. In the upper right, we see a near perfect relationship between increasing heat risk categories and total impacts occurring in each category. The bottom right figure is different. For this particular impact data set, the majority of impacts occurred within the orange category. We can't really know the reasons for this type of behavior, but it doesn't automatically mean a heat risk doesn't work in the area, only that for this particular impact data set, there's a different relationship between the impacts and the method that leverages a 95th percentile type of approach. The decision maker still has very valuable information here. They can take action on orange heat risk days in the future and mitigate that impact in a category where it matters most. For whatever reason, the impacts tail off with increasing heat risk values, and it may be hard to identify why that's the case. A visual consideration with heat risk is that there's going to be artifacts. This is true of any of our weather and impact data, none of it smooth and perfect. We're all aware that PRISM has its own artifacts, such as including non-representative or bad observations, having different details with regard to terrain, thermal belts, lakes. IRMA and RTMA certainly have their share of artifacts, as we all know. Those all feed into the NBM, resulting in issues like cold values over lakes and water areas, bullseyes where bias correction of bad or non-representative observations occur, and of course, the METAR location pixelation issue. Speaking of observations, we have to deal with missing data, station moves, urbanization, land use changes, and so on that lead to artifacts when we place individual co-op station data into a gridded analysis. And lastly, the heat health data going into this approach has its own variability and representativeness to deal with. In short, all of this unfortunately can lead to pixelation and artifacts within the approach. In addition to these artifacts that are quite challenging to mitigate, we also need to acknowledge that combining 3 different weather element grids together and incorporating heat health data into it is just going to result in some blobby and non-smooth behavior. But we deal with those issues all the time with our other gridded analyses, so we should give heat risk some grace when we look at that output. Just the other day, I saw on a weather channel they were providing maps of the supercell parameter, and it was all blobby, and there were places where it was high right next to places that didn't have any values and everything like that. I think if we think about this objectively, a lot of our grids where we integrate data together by nature just look blobby and non-smooth. I'm pretty proud of how the heat risk maps actually look when you consider all of the different things that are going into it that can lead to issues. When we look at our own heat index grids, for example, we also see those fields are also blobby and contain bullseyes and islands. In the example at the very bottom right, maximum heat index values range from 103 to 131 across even this limited domain. So even our heat index fields are neither continuous or uniform. In the West, where heat risk has been available for almost 10 years now, partners are relying on heat risk more and more. Some states like California are leveraging heat risk in their decision processes, including putting up KML files of daily heat risk on their internal dashboard. Media partners are picking up on it and using it in their broadcasts and on their social media channels. Health partners are including it in their own briefings and distribution lists. Heat risk is making its way into planning documents as well, as seen in these examples from Maricopa County's Hazard Mitigation Plan and the California Governor's Office of Emergency Services. Schools are using it to inform their decisions on outdoor activities as well. And the CDC is integrating heat risk into their heat messaging strategies. This simple color-numbered system, along with the lack of any geopolitical borders, have been identified as big reasons for its adoption by a myriad of partners and decision makers. The heat risk service is more than just a 7-day forecast. In fact, I'd argue the climatology of it and the ability to match that climatology at a site with a partner's unique impact information and provide them with those percentages, those historical percentages of where their impacts fall within a heat risk climatology actually are much more powerful than the forecast itself. To help support our partners along with providing valuable background information for the meteorologists, the Heat Risk Service provides a wealth of heat risk climatology information going back to 2005. Via the web page address provided at the top, the main map and the pull-down menu on the upper right are how you access this information. It's important to state that this information is most useful when working directly with partners or used to acclimate yourself to how heat risk is performed in the past. We highly recommend that you do not blast out an email with this link to all of your partners as soon as you install heat risk or get off this webinar, as the information on this page is really science geeky and it probably would generate more questions than solve answers if you just threw it out and provided it to them without your interpretation. That's the big reason this page is not linked directly to the public page, but instead can be accessed by typing in /historical after the public web page address. I've mentioned these annual charts before. Those, along with the Max-T and Min-T daily threshold charts, which have been shown to be of great use when working with partners or getting more acclimated to the approach, are available on this historical page. Annual charts like this one for Chicago O'Hare International Airport easily identifies early season heat around the end of May, with the most impressive heat event occurring between July 2nd and 7th, with a period of 3 magenta days being highlighted in a strip chart at the bottom. This was due to the afternoon temperatures reaching near the all-time record, as shown by that red dot amongst the very highest daily maximum temperature record dots, along with several consecutive days and nights with temperatures in the top 5% of observations for that time of the year. You can also easily identify the periods where HeatRisk would have recommended products, or for the meteorologist to consider a product or enhanced messaging. As stated, we know these are pretty complicated plots, but they do provide a wealth of information for you to look at and learn how HeatRisk performed for notable events in your area. You can also utilize the information to work with partners as you familiarize them with climatological heat risk thresholds and provide them with historical heat risk output at the station level for events of interest. These annual plots are updated weekly, so you can get quick access after an event. Another cool feature on the historical heat risk page are the station-based daily plot maps that you can see on the left side. You can pick out any day since 2005 in a pull-down menu and see the observed point-based heat risk output plotted spatially. You can also add a layer of the Wawa heat products that were issued. This is another great way to explore past heat events. Additionally, the data at each of these points are available for partners and you to work towards linking their unique impact data sets to the climatology of heat risk at a station. You currently need to request this data, but we hope to work on an automated method for retrieving these data in the future. In fact, right now we're working on updating the historical data set. So for now, we're pausing a little bit on distributing the data, but we'll be sending out some information over the next short period of time once we have everything set up. And hopefully it'll be a bit easier for you to request those data. To wrap up my section, I'll provide you with a few examples from last summer of some heat events over the region as highlighted by the heat risk approach, again, forced by NBM day one data. While it wasn't an overly hot summer in the north central US, there were a few periods of enhanced heat events based on a 95th percentile approach, including an early event in mid-June, a major one in late August with more widespread consecutive days and nights, both above the 95th percentile and above CDC informed thresholds, and then a late season heat event in early September with another period of consecutive days of heat at or above the 95th percentile and above CDC informed thresholds. While the temperatures were just a bit too warm in the NBM data when compared to station observations, you can get an idea of how heat risk looks spatially during events such as these. And now I'll hand it back to Kim to bring us home.
Thanks, Mike. So heat risk has been baselined in AWIPS build 23.2.1-46, and we expect all CONUS WFOs to have the baseline version installed by the end of May. No more than 2 weeks after that installation, WFOs should start producing heat risk on a cron and sending it to NDFD. The heat risk grids are generated locally in GFE using Max and Min-T grids from the forecast database, and this is done daily on a cron, as I mentioned earlier, at 1208Z, which also populates the red, orange, and yellow daily threshold levels. So in order to calculate heat risk manually, meteorologists can run the heat risk underscore calculate procedure under the populate menu in GFE. And for offices that use Forecast Builder, they can set the option run heat risk to true in their Forecast Builder config, which will calculate heat risk during the integrity step. And the official rollout of heat risk was just this past Monday, Earth Day. There was a press conference, a press release, a public information statement noting a public comment period, social media post from Weather Service headquarters, and a webinar with our partners from the CDC. We will also have a survey for offices to provide feedback on how you're using heat risk, additional training needs, how your partners are finding it useful, etc. And we'll be sending out that survey after all the offices have installed and set up heat risk with the AWIPS build. So as part of the rollout, We released a new heat risk viewer, thanks to the Western Region developers and WPC. This CONUS viewer for heat risk is an interactive web page that provides you and your partners a way to look at the live heat risk data. As the animation shows, you can move through the 7-day period, click on a location to get the forecast temperatures and the heat risk categories. And you'll also find KML and GeoTIFF layers available for download, as well as further information to better understand heat risk, including appropriate actions to recommend for each of the categories of heat risk. And additionally, by the end of May, heat risk grids will be available for all of the CONUS on NDFD. There's a heat risk VLab site that has a wealth of information. You'll be able to access the plots in the historical website, along with additional information about heat risk itself. And in addition, the VLab site contains training materials, weather story templates, outreach materials, and we have a Google site. You can go directly to the extreme heat section of the site by following the URL at the top, or you can go to the main page and use the hazards pull-down menu to select extreme heat. And we have recorded webinars, training, resources for the rollout, as well as materials and resources for heat index, wet bulb glow temperature, pediatric, vehicular heat stroke, heat safety tips, and more. For external resources, you can point partners to our heat safety page. And there's an overview of all 3 heat tools, including resources and materials such as reference sheets. Then heat risk has many advantages, but it's not the only tool in the heat toolbox. Heat index and wet bulb glow temperature are still used by our partners, decision makers, and general public to varying degrees. And there's no silver bullet for heat. All of these tools should help inform how you're going to communicate heat, be it through social media posts, IDSS briefings, watch warning decision making, and each of these tools play an important role. I should also mention you can, of course, use max and min temperatures. Each of these tools are just another tool in the toolbox as part of the Weather Service Unified Heat Strategy, with the specific focus of intelligent optimization of the heat tools directed towards their most appropriate use. So I encourage you to take this first summer with heat risk, really become familiar with it, see how it can be another benefit to our users, our partners, and our agencies. And I just want to recognize all the folks listed on this page for their tremendous work and dedication towards making heat risk what it is today. Thanks for listening, and we have some time for Q&A.
Thanks, Kim and Mike. We do have a few minutes for questions. If anyone would like to put anything in the chat or raise your hand, we can take it any number of. Joe, go ahead.
Thank you. I have a lot of questions. I do want to say, though, I think that the rollout has been excellent. All the resources provided are awesome. One question I had, Mike, is with regards, or Kim, with regards to kind of the watch warning advisory paradigm. One of the cool things with heat risk is it's one number for the entire day, but there's a challenge there in that, so do we issue a heat advisory for a whole day or an extreme heat warning for a whole day? Do we just do the hottest period of the day? Knowing that like we do have these heat impacts from warm overnight temperatures often, that's like in cooler climates like up here in Duluth, like in Minnesota, where you're dealing with more of the warm nights or more of a heat impact than the hotter days. Are there recommendations from how heat risk has been used in Western region on like the timing, like, and should we aim for some level of consistency with that? Like, you know, should we stick to using a standard set time for headlines, that sort of thing? Yeah.
So Joe, I'll start, and then I'll let Mike add what they've done in Western region. So because Western region has had about a decade of experience with heat risk, they're certainly more advanced. They're more used to it. This summer, we really want offices to look at it. Heat risk should not be the sole thing that you base your watch warning decision making on, because it is experimental for this summer. And the heat risk does not overwrite your regional supplements. And then I will just kind of point that Mike mentioned earlier, the Hill data is that numbers that are not just the whole integer, but actually have, I'll say, more specificity. So you can see how the heat really is impacting the heat risk values overnight or during the day. So I know there's still lots to figure out, but I will pass it over to Mike to at least give Western region perspective and their experience.
Yeah, thanks, Joe, for the question. I have a couple responses here. So the first one I'll say is that when we created HeatRisk, or Heat Impacts Level was the original name of the program, where Hill comes from. The goal was not to replicate or produce a wah-wah generating piece of software. It was that this is a place people go to well ahead of our watch warning advisories to get heads up on what they need to do well in advance of us putting the final nail in the coffin, which is the product itself, kind of a thing. So because we're in a wah-wah world still, we jury rigged it to pump out these recommendations or whatever. But, you know, I'll be honest, out west, you know, where humidity doesn't play as big of a role, we're able to really identify the big days from the moderate days to the low days, and we recommend warnings versus advisories specifically. East of the Rockies, humidity is really, really challenging, and this approximates it. And within the consider, you know, the mid orange to the magenta, the big heat index days are generally in there, but some of the bigger days are in the high end orange, some of the lower days are in red, because there's a lot of nuancy stuff when it comes to heat indices, right? So that's where using both of them together really are quite valued in the messaging. The one area I feel we haven't really been successful with in the West is using those hill grids and our understanding of how heat impacts linger into the evening and overnight hours in terms of the timing of when products should end. In my world, I guess, if the Hill max T grids are red and the min T grids are yellow or orange, then I think doing our traditional, you know, after sunset, you know, kind of a thing is a good thing to do, or 10 p.m. or something like that. But when the overnight mins are orange or red, and I know it's an overlapping category, but what happens, and I think we've all observed this, in homes without air conditioning, the temperatures maximize after midnight. And I just chuckle sometimes when I see the heat, the heat advisory ends at, 7 p.m. and I'm like, oh, the lingering effects last until after midnight. So I've seen some offices now letting them go until 6 a.m. and specifically mentioning, people that live in homes that don't have air conditioning or whatever, the heat's going to continue to build up overnight and opening windows aren't going to work. So we really hope that tailoring the message and looking at everything allows you to better hone in on when you should be canceling these and not just canceling it just at the same time in every situation.
Awesome, thank you. Yeah, we have a lot of homes without air conditioning here on Lake Superior. So
yep, I'm from Wisconsin, so yep.
Yeah, awesome. Thank you, Kim, Mike.
Awesome, thanks, Kim and Mike and Joe. Great question. Anybody else have any questions? You can again type it in the box. Go ahead, NWS Chicago, whoever's there. You're on the
air. Thanks for presenting this. This is really fascinating, and I really like the way you kind of the way the values are normalized across areas where there's potentially relatively significant geographical differences in the impacts in heat over short distances. I think this is a really cool tool for that. And I know it's not meant to encompass everything. I guess I was going to mention one challenge we have here that covering the humidity with low temperatures is a pretty good proxy. One of the things I'll mention, this is more of a Midwest Corn Belt effect, is the effects of evapotranspiration. Results in pretty substantial diurnal dew point curves as well, so that during our heat waves in the summertime, we typically have anywhere from a 5 to sometimes 10 or 11 degree range where dew points peak, maybe in the low to mid 80s during the day and then fall off to low to mid 70s during night. I know this index isn't meant to capture all of this kind of stuff, but I figured I'd throw that out there as something if you're looking to try to improve it a little bit or, customize it to, like I said, it's not a super localized effect, but I think over the Corn Belt, that's pretty common.
Yep. Absolutely.
And I'll just add that, we want to continue having, we have a public comment period and we are asking WFOs to evaluate. So, certainly wanting to get everyone looking at heat risk and see if there are ways to improve it.
Yeah, the neat thing, is that if the dew points are high, because of that evapotranspiration, I'm guessing the mins, during those periods do tend to be a little bit more increase. But at the end of the day, even in urban Chicago, the urban heat island effect's another thing that I get questions on all the time. And I'm like, the thresholds for the NCI climate normals incorporate a little bit of that. But if it's still in the top 5% in urban heat island areas, it's still something that people haven't acclimated to or are used to. And it's still exceptional heat in those areas. But when you go to the rural locations outside of that urban area, the thresholds are quite a bit lower when you do start comparing the station data. So even urban heat island is kind of built into the thresholds as well. And it's surprising, how last year there was an event along the Northeast urban corridor, and you could actually see Philadelphia and New York City and those urban areas popping up in red with orange around it. And it was kind of cool to see that.
Yeah, that's great. And I guess I wanted to, and Kim can help correct me if I'm wrong, but we do have a HeatRisk help chat room that was started, and I forget whose great idea that was, but that is available for folks to share ideas and approaches and messaging, and just kind of kick the tires on this. But definitely adding to the comments during the comment period would be the first route to go.
Yeah, and we are drafting a nice blurb to have your regional program managers note or advertise all the training that's been done, all the regional webinars, and because they were recording all of them, and we will include the URL to that Google workspace, or just put it in the chat.
So it looks like we have time for maybe one more quick question if anyone's got another question. Joe, go for it.
Sorry, I'll ask questions for the next hour if you allow me. I have a lot. Do you have any resources for local offices as we're kind of reevaluating our local heat thresholds and that sort of thing? We have we're obviously not health experts, so we're not used to looking at health data. I'm aware of a few limited data sets. We've tried talking to a few of our public health partners at the county level. Are there any resources available for us to kind of dive into, for example, emergency department admissions data, that sort of thing? Any data sets that you're available, and maybe there is already a list in one of these documents that have been made available as resources, but anything else to help us do kind of local heat evaluation research? We're working right now with our Department of Health on getting some hospital admissions data, but there's a lot of steps. It's made for PhDs. It's not made for random people. Thank you.
So the difficulty with public health data, right, is the PPI and getting that granularity that you need. If there was a big event, then you can perhaps go to the CDC Wonder page and do a little bit of digging there. However, if there wasn't a whole lot of deaths and they don't meet that minimum threshold for help with the protection of PPI, you might be able to get state level data. Another dashboard, which we haven't quite envisioned how to use it, but NEMSIS has worked with CDC to create a heat-related EMS activation surveillance dashboard. We did have them present at the annual public program meeting. So, I mean, go ahead and take a look at that. It does it by, I believe, county level, but it is updated weekly, so it's not like a whole bunch of historical data that you can go back in. But I would definitely suggest that if you, if you can develop those relationships with your public health partners, that just makes it a lot easier because, they are some of the experts. And Mike, I'll let you go ahead and add.
Yeah, I think it's really important to underscore that the use of local data sets is more for helping partners make better decisions than doing a bake-off between heat index and heat risk and things like that. And I will caution very highly that localized data sets are based on death certificates. The way that clinicians identifying people that die from heat is very, very subjective, and it's only the tip of the iceberg. What the CDC has done is their modeling incorporates people that die from cardiac arrest above the baseline, people that die from air quality things. And we can't replicate that at the local levels. And then to maximize it, if you go to any place aside from where you have a lot of deaths or impacts occurring, you need many, many years to accumulate enough data so it's significantly statistically relevant. If you only have 1 or 2 years in a place where 1 or 2 people have died from heat over the course of that, I think the data is going to be very questionable in terms of any usefulness when it comes to that. So I really believe that you need to take that local data. I know we all want to jump into it and do all kinds of, is it working? Here's what we can do or whatever. At the end of the day, I think the best thing is to work with those partners that can provide us with their impact data, to put it into that climatological reference frame. And then again, it's pretty powerful to know more impacts happen in orange than a red or magenta, right? It just means that people are doing the right things in orange and magenta, or magenta and red, or something else. But orange is a category that should be focused on, and they can. I think that's pretty cool to do that. But I'll stop there. But there is a very significant statistical relevance of the data that you're going to run into challenges with, even if you can get your hands on that kind of data, Joe.
That's a great point. Definitely worth underscoring. I think a lot of us have had challenges getting information from local PPI information. So, Vanessa, you have your hand raised. We have time for just a real quick question. Go ahead.
It was more a comment for Joe on the data, and I think it's really what Mike kind of had said. You can get, if you can get the data, it's great, and it's helpful to kind of just get an idea. One of the things we looked at was actually phone calls into 911 dispatch for heat. So that was just one thing to kind of see, okay, rather than looking at mortality itself because of some of those other things. So trying to think of other ways, and especially because, like you said, there might not be a hospital in those counties, or it might be covering, and so the state's not going to give you that data. So looking at even like any places that provide any care within those counties. So even visits, like it doesn't have to be a hospital itself, but there might be a clinic or something that could get, that there might be representation there. So people, it's not the extreme, but it could be, because some of the messaging, that's where the challenge is if we focus on just the mortality portion of it, that's okay. But there's a bunch of people that are being impacted at those other levels. And so that's where the calls and the visits into the hospital and all that kind of stuff. But again, it's all complicated and messy, as you've found. But using the EPH, the CDC is, just environmental public health tracker. If the counties have reported that data, that is helpful. But sometimes a lot of counties don't even report that information specifically because of the privacy concerns. So that is where the limitation is too. But if you can get it, there are different ways to use it. And if you want to talk more about it, I'll gladly chat with you.
Great point, Vanessa. Yeah, definitely.
Also, as we're wrapping up, Gail, I got to jump on another call as well.
Yeah.
But I will also say we're really looking to see different data sets being applied to this. I'm from the Midwest. I grew up on a farm. I would love to see a long-term milk production data set put against heat risk, the categories, and see if there's benefits to a data set like that. Or I can list off a whole bunch of different data sets that aren't based on human health. That would be pretty cool to see how they relate to this, as long as you have enough data to perform that.
That's awesome. There's a lot here. There's the messaging, reaching the vulnerable groups, non-human impacts, all sorts of stuff. I will close it off at that and hand it back, I guess, to Jess to handle the closing out. Thank you, Mike.
Yeah, I think we're all good here, and we'll just let Mike Myers close down the recording. Thank you, everyone, for coming. And yeah, feel free to reach out to public.program@noaa.gov if you have any additional questions.
Yes, Jessica mentioned, thanks for attending. Great job by our presenters. That will end our recording for today.